Make sure you listen careful. Our last topic is about energy and how it impacts the environment. Sometimes energy comes from the environment. Sometimes the energy we have impacts the environment, sometimes in positive, but most of the time it's in negative ways. And so what we want to do is talk a little bit about that today. So my first slide here basically talks about energy consumption. I already showed you guys, even in our lab, one of the mechanisms in which we create electricity. It was in 1831 that Faraday discovered the principle of electromagnetic induction. The basic concept behind electromagnetic induction is that if you take a magnet and a wire and you move a coiled wire and a magnet next to each other, you can create electricity. And I showed you guys that at the back table there last week whenever we did our lab. I took a coil of wire, I put a magnet in and out of it, and by doing that, it created a small amount of current. Now, scientists managed to figure out, well, it doesn't work really well if I always have to be the person to move the magnet or move the coil of wire. But if we can have the environment do it for us, and we can spin a coiled wire inside of a magnet, we can generate electricity. And that electricity is what we then use to power everything around us, right? So that's what I have on the slide right here. Now, the three most common natural sources are either going to be tides, hydroelectricity, or wind turbines. And all of those are natural ways in which we can cause the environment to spin something around in a circle. However, there is another source that we have for creating electricity, and it's called burning fossil fuels. And it's really big in the news these days because we've discovered that when you burn fossil fuels, although it can create electricity for us and create energy and create heat, it also releases carbon dioxide. And maybe you guys have heard both Canada and all the provinces in Alberta are starting to impose things called carbon taxes, where because carbon dioxide is hazardous to our environment, we want to try to prevent that. So that's what I want to talk about on this slide right here is that a lot of our electrical power, though, comes from burning oil, coal, or natural gas. And basically, in this picture here, I'm trying to describe how it works. Here's what they're going to do. You are going to try to burn or heat some sort of fuel in this kind of area right here. Whether it's a natural gas, an oil, a coal, whatever it happens to be, you're going to burn it. And when you burn it, it's going to create heat, which is good. We often need heat. What it's going to do in this system here is it's actually going to create steam. It's going to take water and turn it into water vapor. And that steam is then going to go through like a pipe system here. And that steam is actually going to push a turbine and cause it to spin. In the exact same way that wind can make a turbine spin, or water power can make a turbine spin, you can make steam push a turbine and spin it around in circles. Well, if this turbine spins around and around in circles, if you attach to it over here, say a coil of wire, and have some magnets on both sides of it, that's your generator. This is electromagnetic induction. It'll create electricity. And really what ends up happening is that steam runs through this loop, where once the steam pushes the turbine, it gets recooled back down into water, and then it gets boiled and turns back into gas, and it basically keeps the turbine continuously running. Now, in Alberta, a lot of our energy is actually based on burning natural gas or burning some sort of fossil fuel. Ideally, in an ideal world, we'd love to get into solar panels, we'd love to get into pure wind power, but a lot of the problems associated with those is that they're not consistent. For example, how good is a wind turbine when there's no wind? Right? How good is solar panels if it's a cloudy day? You know what I'm saying there? And so there's kind of a trade-off. Usually fossil fuels are cheaper and very reliable, but they're not as good for the environment because they release carbon dioxide, and that's why we have carbon taxes. So that's what this slide is about, basically. Have you guys ever heard that phrase, fossil fuels? Is that a term you've heard at some point before? If you haven't heard it before, the reason why we call them fossil fuels is that oils and natural gases, they actually are remnants of decaying plants and matter, usually from like the dinosaur era. And it's fossils that have actually eventually died and through lots of pressure and lots of temperature have eventually turned into a gas or into an oil of some kind. So that's why we call them fossil fuels. What I've got on this slide right here is some other ways that we can generate electricity. We don't just have to burn fossil fuels, but here are some of the other methods. I already talked about wind, hydro, solar, and tidal a little bit. Those can all be used to pump a turbine and move a generator. Do you guys know what geothermal energy is? Anybody ever heard that before? What is geothermal energy? Could you give a brief summary? Yep. The Earth itself is actually got a lot of heat to it, especially if you go further and further down underground. If you ever heard of a term like a geyser, like say Old Faithful in the United States, if you know what that is, it's a geyser which basically shoots up steam and a lot of hot air from deep inside the Earth's crust. And if we can find a way to harness the Earth's own natural heat, we can use that to create electricity. So that's what geothermal is. Biomass. I actually showed you guys, I think, one of my Science and Society articles was about biomass. Did I talk to you guys about the one how there was a project in third world countries to take literally human waste, take poop, and to turn it into fuel? You guys ever talking about this at all? That's biomass. It's where you take organic material. Usually, it's left over from like say cattle or horses or something like that, and you take their waste, and we try to find a way to burn that. And hopefully it's not going to be what's the best way of saying it? It's almost like it's recycling in a way. Does that make sense? Where it's something that you normally would throw away, but if we can turn it into a fuel, then that's called biomass. What I'm going to suggest on this slide right here, go through your textbook and maybe find the definitions out of your textbook, because these are all going to be bolded words that are in your textbook. So rather than me writing them down, though, I'm just going to leave that for you guys. I'd like you to know about different ways of generating electricity. But at the end of the day, they all kind of run through the same concept. It's electromagnetic induction. A turbine spins, and in that way, it causes a coil of wire to spin around inside of a magnet, and that's what creates electricity. In general, then, of all the ways that we try to make electricity, we usually break them up into one of two categories, and you've probably heard this before. But if you haven't, here's the gist of it. We either call it a renewable resource or a non-renewable resource. A renewable resource is something that can last for forever because that resource keeps coming back. Like, for example, wind. As much as we use windmills and like wind turbines in southern Alberta, it doesn't make the wind like get used up. The wind doesn't just die and end because of the fact that like we use turbines on it. Does that make sense? And so that for that reason, it's renewable. The sun, solar power. The sun is not really going to die anytime soon. It's supposed to last for billions more years. So those are renewable resources. Whereas all of our fossil fuels, once we use all of the oils and coals and the tar sands in Fort McMurray, once all of that gets used up, well, that's all there is. Does that make sense? That's what makes something a non-renewable resource, is that it can literally run out at some point. This one right here, I put a little asterisk next to it. Trees usually fits into a renewable resource, but we have to be very careful with trees. If we were to clear-cut forests all the time, we might get to the point where maybe we would start to run out of trees. But the cool thing about trees is that they can be replanted. You can always plant more of them. Does that make sense? So trees do fit into the renewable resource section as long as we're careful enough to not eventually have like entire forests get clear-cut and die, right? But the cool thing about plant life is that it will actually regrow new stuff in its place. Even when we cut down a forest or forests burn down naturally, they'll grow back. It takes a while, that's all. Here's a slide that really just talks about the reason why burning fossil fuels is bad, though. Have you guys ever heard the phrase the greenhouse effect? It was discovered back in like I want to think 80s to 90s, where they realized that similar to a greenhouse is supposed to get very warm inside of it, and hopefully plants can grow inside a greenhouse quite well due to trapped heat. The problem is that Earth as an ecosystem, if it traps too much heat, we undergo global warming, which is a huge thing these days, is that ocean levels are rising, and there's actually some islands that are literally going underwater because of the fact that the Earth is getting too hot. The basic idea is that as light comes from the sun, it's supposed to reflect. Some of it's supposed to get absorbed by our atmosphere, and some of it's supposed to actually leave our atmosphere. But as we add more carbon dioxide inside, which is known as a greenhouse gas, it causes heat to, rather than leave the system, it actually sticks around. And so Earth keeps getting hotter and hotter and hotter, and that becomes a bit of a problem. And so we've attributed a lot of that to carbon dioxide. There are other greenhouse gases as well, but carbon dioxide is really the big one these days. Does that make sense? Is that something you guys have heard before in your lives? The whole carbon dioxide, carbon emissions problem? So the last thing I need to talk to you guys about today then is, well, what sort of ways do we have to try to reduce the amount of impact on our environment? And so The biggest one is that we need to pick machines that are very efficient. And I threw a picture on here. A big thing these days is to change light bulbs and to change your devices to energy efficient ones. Um, yeah, I think this is like some department store, probably Walmart. Right? I didn't take it. No, I found it online. Right? But you guys see these light bulbs right here. One thing I want to point out is that old-fashioned light bulbs, they used to be like 100-watt light bulbs. And you can actually see it says 100 watt. But like newer efficient light bulbs, the way they work is that rather than using 100 watts, they still provide just as much light, but they run on, say, 26 watts. And that's what these are actually advertised as. They're being advertised as only using 26 watts, and they're being used as a replacement for what used to be a 100-watt bulb. You guys ever heard or seen that before? Does anybody know what a watt is? Because that's the last part of my lesson. Yeah. Yeah. A watt is basically a measure of how much power something uses. And if we can, we want to use things that are energy efficient. So on my next slide here, I want to talk about how we measure efficiency in different ways. And the first one is power. Okay? Power is basically how much energy something draws. Okay? The technical definition here is power is the rate at which a device converts energy. Okay? And the technical definition here is a watt is equal to a joule per second. Okay? And so if you have a device that uses 5 joules per second, that's not a whole lot. If you have a device that uses 1,000,000 joules per second, that's a battery drainer. Say that again. If you have a device that uses 5 joules per second, that's not a whole lot. But if you have a device that uses 1,000 joules per second, that's going to drain the battery on your device, or it's going to use a lot of electricity. Does that make sense? So the higher the wattage, the more electricity that it's draining and the more electricity that it's using. And ideally, you don't want to have a high wattage device then. So when I go back and I talk to you about light bulbs right here, if you had to use a 100-watt light bulb or a 26-watt light bulb, you'd rather use 26. Because 26 watts only uses 26 joules every second, as opposed to 100 joules every second. Does that make sense? And so what we really want to try to do is limit how much energy you need. Use energy efficient devices. So here's the formula that's on your guys' formula sheet. If you guys have your old periodic table, this is what they're going to give you on the PAT. This formula here, E equals P times T. E is how much energy you use. P is the power rating on the device. And T is how much time you use it for. And I have to point out this has to be in seconds. Okay. If the time is not in seconds, this isn't going to work properly. And so I'd like to just show you a couple examples of a type of math equation you might get asked to solve. So I've got one right here. Let's say that you have a microwave, and that your microwave, on the outside of it, it says it's an 800-watt microwave. Here's what that means. It means that every second it uses 800 joules. Every second it uses 800 joules, which is a lot of energy. I would rather use a 5-watt device because it means it only uses 5 joules of energy every second. You know what I'm saying here? But, okay, so fine. It's an 800-watt microwave. The question is, how much energy are you going to use if you cook popcorn for 2.5 minutes? So the formula you're going to use is that energy is equal to power times time. That's the formula I gave you on the previous slide. The power that we have is 800 watts. So this is 800 right here. Here's the issue, though. Time, though, has to be in seconds. Yeah, so we just got to convert 2.5 minutes to seconds. The best way of doing that is to say there's 60 seconds in a minute. So if you times 2.5 by 60, 2.5 times 60 is 150 seconds. So 180 watts times by 150 seconds means, I'll grab a calculator here. Yeah, 120,000 joules. That's a lot of joules. Now, one of the things I need you guys to know how to do, though, is to be able to convert between a joule and a kilojoule. In your math class, my understanding is you guys have learned about things like centi, deci, deca, some of those sorts of things. I'm going to skip ahead in my slides a little ways here. Have you guys seen one of these pictures before where there's kilo, hecto, deca, deci, centi, and milli? You guys haven't done this in your math class before? Okay. Okay, so if you guys do remember this from a previous math class, that's awesome. If not, can I give you a quick tutorial here? This is what I need you guys to know for this class here. We often work in kilowatts or kilojoules. So here's the basic thing you should write down. If you want to convert from kilo into like something normal, you need to times by 1,000 or you need to divide by 1,000 if you're working with like a kilo something. The question is, though, you just got to figure out whether you want to times by 1,000 or divide by 1,000. Okay. If you were trying to turn it into a kilo, so if you want to go into a kilo something, oops, I can't even spell it, then you have to divide by 1,000. And if you're going from a kilo something into a normal unit, then you times by 1,000. That's basically the principle. You either have to multiply or divide by 1,000. Okay. If I can go back to this slide right here, this amount of joules is a lot of joules. And so rather than measuring it in joules, a common thing to do would be to measure it in kilojoules, kJ. All you've got to do then to convert to kilojoules is divide by 1,000. So if you take 120,000 and divide by 1,000, a more likely way of answering it would be to say it uses 120 kilojoules of energy. All you have to do is divide by 1,000. You guys remember doing this at all before? Okay, it's not familiar, huh? I'm going to close the door while the grade 6s are out there. So, if you have a very, very large number, divide by 1,000 and call it a kilo something. So if you have a lot of grams, divide by 1,000, now you have kilograms. If you have a whole bunch of liters, divide by 1,000, you now have a kiloliter. Okay. So the only thing you guys need to be able to do in this course is do kilo. So if you've ever heard of centi or milli or hecta, we don't even do those ones. I just need to be able to do kilo. Okay. So either multiply or divide by 1,000. Let's try another example here. One of the ways in which we measure energy on our homes, anybody ever see one of these on the side of their houses? It's a device that keeps track of how much energy your house uses, and then the energy company will then bill you based on how much energy you use, right? It measures things in something called the kilowatt hour. And basically the way it works is that they measure how many kilowatts you use, and they multiply by how many hours you use it. And so rather than measuring things in watts, they measure them in kilowatts. So what I'd like to do right here actually is calculate the exact same example. It's actually the exact same one right here, but we're going to measure it in something called kilowatt hours. Okay. Now this is really easy to do. To measure something in kilowatt hours, you have to know how many kilowatts you have, you need to know how many hours you have, and you just multiply the two of them together. So this number right here, the 800 watt microwave, if I want to convert it to a kilowatt, do you guys remember again how to convert something to a kilo? To convert to a kilo, you need to divide by 1,000. So if this number here was in watts, to convert it to kilowatts, just divide by 1,000, and you're going to end up with 0.8 kilowatts. So if I want to get this into kilowatt hours, I need 0.8 kilowatts. Now, normally we measure things in hours because that's a bigger unit of measurement. Okay. But if you only cook on your microwave for 2.5 minutes, we need to convert that now into hours rather than into seconds. So 2.5 minutes. How do you convert from minutes to hours? How many minutes are in an hour? Okay, so you need to divide this by 60 then. 2.5 minutes divided by 60 minutes in an hour means that 2.5 out of 60 is 0.0416. Repeating, it's that many hours. Right? Like 2.5 minutes is not very much of an hour. So to calculate a kilowatt hour, all we've got to do then is take the kilowatts and times by your hours, and that'll tell you how many kilowatt hours you've used for energy. I ended up getting this. When I times 0.8 by 0.416 repeating, I got 0.033 repeating. That's how many kilowatt hours it would be for you to use your microwave for 2.5 minutes. The way the power company works then is that they charge you a price per kilowatt hour. I don't remember exactly what mine is right now. I want to think that it's like a couple of cents per kilowatt hour. So like it costs me 4 cents per kilowatt hour. So that if I want to figure out how much my electrical bill is at the end of the month, they will add up on a meter like this how many kilowatt hours of energy my house has consumed, and then they'll charge me by the price, 4 cents or 10 cents or 0.3 of a cent. Does that make sense? Well, it sounds like it's cheap, but then when you think about how many kilowatt hours we use, this was just for 2.5 minutes of microwaving something. Now my lights are running, my dishwasher is running. We were watching Netflix for 7 hours yesterday, so my computers were running. You know what I mean? Like, anyways, just about average. Anyways, you guys get the point I'm trying to make here is that when you start adding it up, we actually use a lot of kilowatt hours of energy. So here's what I need you guys to be able to do. I need you guys to be able to use this formula back here, the one that is energy is power times time, to calculate energy in joules. Or I need you to be able to calculate a kilowatt hour, which is the exact same thing, only rather than it being in watts and seconds, a kilowatt hour means you have to convert it to kilowatts and hours. Both of them really work the same way. You're still multiplying two numbers by each other. It just depends on your units. So hopefully I was able to make it clear today. If you want to convert into a kilo something, all you have to do is divide by 1,000. Okay. Now, the final thing I got to show you then is, well, then, how do you know how much power a device has? I told you in that last example that your microwave was 800 watts. But how do we know how much power a device actually uses? Well, here's one final formula. This is another one on the back of your chemistry periodic table. It is the way we calculate power is you take the current and you times by the voltage. Quick review again. What is current? Well, current is about like how much electrons can flow. Okay, if I use the water tower analogy, if there's a water tower up here and I poke a hole in it and water starts leaking out of it, if I poke a little hole in it and water just drips out one drop at a time, that's not a lot of current. But if water is able to gush out and like come out really easily, that means you have a lot of current. Current yesterday is actually what was causing some of your batteries to light on fire. Anybody have a battery light on fire yesterday? It's because you had too much current. If you have too much current, those electrons are flying through the wires so fast that eventually they light on fire. That becomes a bit of a problem. So we have to make sure we limit current. And you guys also should know from me teaching you that current is also what's dangerous to humans. Because if you ever have too much current pass through, it's actually what can stop your heart. So current is like how much and at what speed the electrons are kind of flying through the circuit. Voltage is like the energy that they're given. It's like the initial push they're given. And voltage would be like, if you use that same water tower analogy, if the water tower were this high above the ground, that's not a lot of voltage. But if the water tower were this high above the ground, as all that water falls out of the tower through the leak that's there, it's falling further. So therefore, there's going to be more energy to them. Another analogy I might give is the hallway analogy. If I were to have you guys try to go between here and the office, if the hallway was literally like this narrow and there was like one person could walk at a time, we wouldn't have a whole lot of current because it's not possible for you to walk. You might have to walk like in a single line, especially if like all the grade 6s are out there, right? If I had a lot of resistance, then you might have to walk single file through the hallway. That's limiting our current. Whereas right now, since the hallway is empty, like 19 of you guys could walk down the hallway no problem. You get what I'm saying? That's current. More of you can travel at once. Voltage is how much energy you have. So imagine I gave you a push to get you going. If I gave you a little push, that's a little bit of voltage. If I give you a big push to get you moving, that's a lot of voltage. So anyways, long story short, if you get the idea of current times voltage, if you multiply the two of those together, that's how you get power. What I need you guys to know then is that of the formulas that you're given, there's a link on both of them. Power is current times voltage, but power is also in this other formula back here. So I need you to be able to work with power from two different directions. One involves energy and time, and then the other one involves voltage and current. So let's try another example here. Let's say that you have a hairdryer that is a 1,000 watt hairdryer, and you plug your hairdryer into the outlet, and we know that regular household electricity is 120 volts. My question for you then would be, how much current is running through this? So we need to use this formula here. The amount of power you have is current times voltage. Now, if I start plugging in some numbers, I actually know how much power there was. I know that power was 1,000. I don't know current. Current is represented by I, so I actually don't know I. But I do know that my voltage was 120. We just need a little bit of math skills here. We need to be able to isolate I by itself and solve for the one unknown variable. Now, again, I don't teach you guys math, but my understanding is you guys have done a little bit of algebra before in your lives, right? Okay, I'm glad. How do you get I by itself? What do you have to do to get rid of this 120? Do you guys know? You have to divide this side by 120 and divide this side by 120, and that will get I by itself. Yeah. So all you got to do here to find current is take 1,000 watts and divide by 120 volts. And it's 8.333 repeating. And then the unit we would have is amps, because that's what current's unit is in. So I need you guys to be able to use these formulas here. And if I give you 2 out of the 3 variables, you're going to be able to solve for the remaining one. So in this example here, I gave you power as 1,000 watts. I gave you voltage as 120 volts. To get current by itself, you have to divide by 120 on both sides, and that'll get you how much current there is. Just so you guys know, 8 amps of current is plenty. It's more than enough, which is why you shouldn't, like, for example, drop your hairdryer into the bathtub. It would be enough to electrocute you. Does that make sense? So that's why water and electricity don't mix. Okay, the last formula that's on your formula sheet that you guys are going to get when you register at your PAT is about efficiency. And this is the final one below. Yeah, it's the last one on there. The way you calculate efficiency is very easy. It's almost like how you calculate your test marks. Can you be quiet, please? Okay. The way you calculate efficiency works like this. You calculate how much output a device gives you. You divide by how much input you gave it, and you times by 100. That'll give you efficiency. Let me show you in this photo how this works here. Let's say that you input 100 joules of electrical energy. Okay. However, the light bulb only gives off 5 joules of light. The way this would work then is that you only got 5 joules of light out of 100. 5 out of 100 is 5%. This light bulb is only 5% efficient. Where's the rest of the energy go? Yeah, heat. The biggest reason why is that many things have friction, and friction causes heat to be lost. Okay? It's actually that same reason when you guys were making your circuits yesterday, the reason why many of them caught on fire as you were playing around is that sometimes there's so much friction and so much lost energy due to heat that eventually it rubs so much that it'll actually ignite. Does that make sense? And so that friction, that lost energy due to heat, if it gets hot enough and hot enough and hot enough, it might actually start sparking. So we want to try to find devices that are very energy efficient, which means that we want to have high efficiency percentages. I've only got a few slides left. I'm almost done here. Let's try another example here. Now, when I originally made these notes, I actually made a typo. So I wrote a little note on here. I had to change a number. Can you guys look at the notes in front of you? Did I change this number right here? It used to be like 30? 38. Okay. Can you guys change it in your notes to 34? I had a typo in my notes. Change it to 34 kilojoules of thermal energy. Okay, so here's one of our last examples. I'm almost finished, guys. Make sure you give me your attention for a few more minutes, okay? Let's say that you have a 300 watt hot plate. 300 watt hot plate. What does 300 watts mean? It means it tells us how much energy it uses. It uses 300 joules every second. That's a lot of joules every second, right? I mean, it's not quite as much as the 800 watt microwave, but it's certainly nowhere as good as, say, like a 16 watt light bulb, right? The higher the wattage, the more energy it sucks, the more energy it drains. Does that make sense? So this is a 300 watt hot plate. Now, we're going to run it for 2 minutes. We could then use one of our first formulas we learned. I believe it was the amount of energy you get is about how much power you have times by how much time there was. So I could calculate for you how much energy it uses. 300 watts needs to get times by time. But time, though, in this example is going to want to be in seconds still, though. How many seconds are there in 2 minutes? Yeah, 2 minutes is 120 seconds because you just got to times by 60, right? So if you take 300 watts and you times it by 120 seconds, this will tell us how much energy it uses. Because remember, every second it uses 300 joules. So 300 joules times by 120 seconds means this guy right here was soaking up 36,000 joules of energy. That's a lot. And that was only 2.5 minutes. Actually, this was only 2 minutes. Now, once again, though, I have the same issue. This is such a big number that rather than using joules, it might be more effective to measure it in kilojoules. Yeah, so divide by 1,000. Divide by 1,000 and it's 36 kilojoules. Now, what I want to do here, though, is I want to be very specific. This 36 kilojoules is how much energy it sucked up. This is actually the input. It drained this much energy from my power bill. Does that make sense? Like, I have to pay for 36 kilojoules of energy. That's how much energy I used. Now, here's the thing, though. Every device is not 100% efficient, though. Some devices are less efficient than others. This guy right here, it only actually gave me 34 kilojoules of heat. So for my final calculation, if I want to figure out my efficiency, the formula for efficiency was the input. What was it? It was output over input times 100. Here it is. So it's output over input times 100. Now, the output is up here. It only gave off 34 kilojoules of energy. But we just calculated that I had to pay as though I used 36 kilojoules of energy. How efficient is this device? 34 out of 36 actually isn't that bad, is it? It's pretty good. It's not 100% efficient, but 34 out of 36 as a percentage, just like on like a test, if you got 34 out of 36, you were 94% efficient. That's not bad. Yeah. Now, I mean, there's a lot of devices, though, that are not efficient whatsoever. Like, say, like a car. A car is actually like only like 20 or 30% efficient. A lot of energy actually gets wasted by heat. Okay? And so I'm actually just about finished. I think I only have one slide left. This slide right here I found, it actually shows you a whole bunch of devices and how much their outputs and inputs compare to each other. Why don't you look at this one right here? If you were to have a gas-powered SUV, you need 600. Yeah, stay with me, please. Shh, I'm almost done, and I can't yell over top of you. You need 675 joules input, and you only get back 81. If you were to calculate its efficiency, an SUV is 81 out of 675 times 100. That's only about 12% efficient. Yeah. Whereas if you had a hybrid, it's 195 out of 675. It's about 29%. Oh. So anyways, I've got some different things on here that tells you different devices. What I need you guys to know is that there's no device that's 100% efficient, but that's what we're aiming for. And I want to go back to this picture right here before I finish. In order for us to be more energy efficient, it's important for us to pick energy efficient devices that use low wattage. Okay? If you guys have like old light bulbs in your houses, like not the newer ones that look like this, nice little spirally ones, but like the old ones, some of them are like 110 watts, and they use a ton of energy. But like newer efficient ones, I think I bought light bulbs the other day that were like 7 watts, which is way, way, way more efficient because I have to use less energy. So it's really important, if you can, don't use 100-watt light bulbs, use 26-watt light bulbs, or if even better, try to get away with 7-watt light bulbs. Apparently. All right, I think that was my last slide, right? Okay. So, guys, let me do a quick summary here, but we're done our unit here. So give me your attention for, say, 2 more minutes, okay? And then I'll be quiet. My voice is starting to die anyway, so shh. Here's what we learned about today. I think I can break it down into about 3 things. Okay. The first thing you guys need to know is, where do we get our sources of energy from? Many of them are, ideally, they would be renewable resources, like, say, hydroelectricity, solar panels, wind power. That would be great. But a lot of the things we do are actually non-renewable resources, which is where we burn fossil fuels. Either way, when we make electricity, it happens the same way, though. We run a turbine that causes spinning coils to run through magnets, and that's what makes our electricity. So that's thing number 1. You guys should know how we make our electricity. Okay. The second thing I need you guys to know is all about power. Shh, please. Because I have higher expectations of this. Power is the next thing I need you guys to know about. Power is all about the rate at which you use electricity. If you have 100 watts versus 5 watts, 100 watts sucks so much more energy than 5 watts does. So ideally, you're looking for a lower wattage. Okay? I showed you 2 formulas that involve power. One of the formulas is that power is current times voltage. The other formula is that the amount of energy you have is the power times time. Okay? I need you guys to be able to work with both of those formulas. And on your assignment, there's lots of practice questions. I highly recommend, when I'm done talking in a few minutes here for the last half hour, you should really try some of those questions in practice. The third thing we talked about is efficiency. Ideally, you want to have a nice efficient energy device, which means that hopefully it's like 99, 95% efficient. But there are many things that are only like, say, 12% efficient. It's really easy to calculate efficiency. All you got to do is take the output and divide by the input, just like you do on a test. If you got 9 out of 50 on a test, just go 9 divided by 50 times 100. Okay. Those are the 3 things we learned today. So let me leave you guys with this thought then. Of all the things you have to work on, I strongly recommend start working on your assignment if you haven't already. Hopefully you have. In your physics assignment number 2, if you get as far as the back side of the page here, I would really recommend trying, like, say, questions 11, 12, 13, 14, 15 today. The reason why is that's exactly what we talked about right now. So even if you haven't started your assignment yet, I might recommend go do these ones right now. I'll even do one of them right now with you. Number 11. Grab a sheet of paper. I'll do number 11 right here with you. Why? Sorry. Do number 11. I'll do 13 with you in a second, Dylan. Okay, number 11. I'm going to give you 1.5 amps. I'm going to give you 120 volts. Your job is to find power. This is actually super easy. The formula for power is current times voltage. All you have to do to calculate this one right here is take 1.5 amps and times by 120 volts. What's 1.5 times 120? Grab a calculator. What is 1.5 times by 120? 180. There you go. 180 watts. Okay, you're done a question. Okay, guys, I'm going to stop now. You guys have half an hour. Use this time, okay? Please, use this time to do well. Okay? I'm done. You guys have 1 week until our unit test now. Thank you, guys.
Question 9.